this figure is taken from Patfield book. What the kind of maneuver we are talking about is, see, the helicopter goes in a spiraling path, but it can have a side slip also. Okay. Now, if this is the kind of motion, how do you trim the helicopter? Because it is a very complicated maneuver, not like our what we solved the earlier level flight. Okay. But if we solve or if we formulate the equations for this problem, then you will be able to solve any problem which will be a simplified version of this. So, essentially the helicopter attitude can be anything, and the velocity vector Vf is oriented in space, and that vector is also turning. Okay. Now, the flight speed is given by velocity vector. You may say that is a constant, the magnitude is a constant, okay, and you will specify a flight path angle. That is, you have to define what is that flight path angle, because this vector is oriented in space in some direction. And then you also define one turn rate, the rate at which the vertical from the helicopter how the helicopter is spinning. You can say turn rate, spin rate, anything, but that is about a vertical axis. Okay. And of course, one more quantity you specify the side slip. We will define what side slip is. Now, only these quantities are specified. They have nothing to do with the type of equation we are looking at. But if you see overall for this type of a maneuver, you have to treat 9 equations. Okay. Those 9 equations are 3 force balance equations and 3 moment balance and then another 3 kinematic relations. Okay. Now, force balance, moment balance, you know, for a rigid body, because you say F is equal to m, that is Newton's law, and the moment balance is moment related to angular acceleration, etc. But the kinematic relation represents essentially the instantaneous angular acceleration, or sorry, angular velocity, instantaneous, because at every instant the aircraft is turning. So, it will have an angular velocity which is a vector, but how that angular velocity vector is related to the orientation rate of the helicopter with respect to some earth fixed coordinate system. Now, this is like orientation of the helicopter is one, angular velocity is another. How do we relate this? This is where you have to have now coordinate systems very precisely marked. First, you write the body fixed system. Okay. Body fixed coordinate system. Okay. This is basically you take the helicopter, you and the Please note I am using slightly different coordinate system for this case, because this is what generally most of the flight dynamic people use. X body, and then this is y body, and then this is z body. This is the center of mass of the helicopter. This is body fixed coordinate system. That means when the body turns, this axis system also turns, and this is attached to the center of mass. Okay. No, z is going down. Okay. You can take this as the dash dash dash. This is going in. This is into the board. So you can say XB ZB is in the plane of the board. Okay, this is a standard thing. Now, how do I get this? This means you have to first define a earth coordinate system. Earth coordinate system, you can say this is my X earth, Z earth, and then this is Y earth. Okay. You can have this any direction, local. Now you see the sequence of rotation from this to this is actually you follow yaw, then pitch, then roll. Okay. And yaw is psi, I think then it is theta is pitch, and then phi is roll, yaw, pitch, roll. This is the sequence, all counterclockwise. So, that is what I have shown here. If you look at it first, this is the Z earth, X earth, Y earth. I give a psi rotation counterclockwise. I get the coordinate system x1, y1, and of course z1 is same as ZEA. Okay, I am not writing the transformation matrix fully. Then what you do is you take y1, x1, z1, give a pitch rotation, then you will get x2, z2 and y2, y2 and y1 will be same. Next you go to the roll about x2. Okay. Now this is the sequence of transformation. If you follow this sequence, this is a very well set all the orthogonal transformation. I will just finally write the transformation between, this is the xb, yb, zb, this is cosine theta, cosine psi, then cosine theta, sine psi, sine theta, then sine phi, sine theta, cosine psi minus cosine phi, sine psi, then sine phi, sine theta, sine psi plus cosine phi, cosine psi, and then this is sine phi, cosine theta, and here cosine phi, sine theta, cosine psi plus sine phi, sine psi. This is cosine phi, sine theta, sine psi minus sine phi, cosine psi, and then cosine phi cosine theta, and this is x earth, y earth, z earth. Okay. This is the full, because this you may find in textbooks also, this transformation, because this is just a product of 3 matrices, that is all. But follow this sequence, that is the most important thing, yaw, pitch, roll sequence. Okay. Now, what is the angular velocity of the helicopter? At any instant, you define by angular velocity of the helicopter as p e x b q e y b plus r e z b. Okay, that E is the unit vectors. Okay. Now, this is the instantaneous angular velocity vector defined with respect to body axis. Okay. Now, you will see, if you want to know what is the angular velocity vector, but defined in terms of time rate of change of these angles, because when the body is rotating, which means they are also rotating with respect to the earth axis, but you will find the same omega, you can write it as, I am putting it psi dot E z earth, because this is with respect to the earth, and then plus theta dot E y 1, because look at this, theta dot is y 1, plus phi dot E x 2. Okay. These are time rate of change of orientation of the vehicle as defined by my yaw, pitch, roll sequence. Okay. Because yaw is about the ZEA, this is about the rotated y1. Now, what you do is you make a transformation of each one of them to body axis, because you will find each one is the intermediate position. You can get the transformation from ZA to XB, YB, ZB. Y1 also you can transform, but this is actually the body, phi dot is along the body. Okay, because that is a x2 which will be the body axis. If you do the transformation, you will get this relationship. Maybe I erase this part, here I will write. The relationship is, finally you convert everything into XB, YB, ZB. Okay. You will get P equals phi dot minus psi dot sin theta, and Q equals theta dot cosine phi plus psi dot sin phi cosine theta, and then R is minus theta dot sin phi plus psi dot cosine phi cosine theta. So, this is the relationship between instantaneous angular velocity to rate of change of the orientation angle, but please remember this relation is not, they also depend on what is the theta and phi. That means you have to solve for the orientation angle. Okay, this is a nonlinear relationship, okay, because that is theta dot is there, then there is also theta. So, this is where solving this problem is this is what navigation, even satellite communication, navigation, everything, this is what is used. Okay. So, now you have a relationship between instantaneous angular velocity to orientation of the vehicle, because orientation of the vehicle can be with respect to earth axis in any orientation. You always want to know what orientation it is there. So, particularly if you are designing autonomous any vehicle, you have to know all this and the estimation of this. Okay. Now, you can always solve for this in terms of PQR also. That is like you take, because psi dot, phi dot, theta dot. Okay. You can get it in terms of PQR, but again theta will be sitting, theta and phi. So, this is like just a transformation of one to the other coordinate. We will not use that. Now, what I want is the body, what I specify is my velocity vector, I will specify velocity vector of the helicopter, which is actually I define my velocity vector as u e x b plus v e y b plus w e z b. That means, this is my u v w and you have p q and r. Okay. So, at a time I have a velocity of the body and the angular velocity of the body defined with respect to body fixed system. Now, if I want, yeah.
Again, like the theta, phi and psi.
Yes.
Now they are with respect to what point?
As you have defined here. Okay. That is why that sequence, you follow what sequence, that is the most important thing. This is the sequence we are following. Suppose if you change the sequence, you will find a different thing. Usually that is why I said yaw, pitch, roll sequence is followed. So that the convention everybody understands this, and the coordinate system also they try to use the same thing. Okay. Now the question is, I have the velocity and the angular velocity, translational, angular, all. Now I can go and calculate what is my acceleration of the center of mass. Okay. So maybe I erase this part, because this transformation I use it as a transformation from this coordinate to this coordinate, that is all. Okay. Now my velocity is velocity of the center of mass is u e x b v e y b plus w e z b. Now what is my acceleration of the center of mass? Time derivative of this, and then these vectors are also changing their orientation, but they change with the angular velocity. So omega cross v will come. So you will have u dot e x b plus v dot e y b plus w dot plus omega cross v. Okay. Now you put the omega is there, PQR, you use PQR, do not use this omega, because that we will keep it as a separate relationship. Okay. Always use PQR, take a cross product, you will have the acceleration of the vehicle. Vehicle I will write it here, this is u dot minus r v plus q w e x b plus V dot minus P W plus R U E Y B plus W dot minus Q U plus P V E Z B. Okay. So, I have my acceleration. Only thing is I have to now apply Newton's. This is the absolute acceleration of the mass. So, what are the loads that act on the helicopter? You have a main rotor load, tail rotor load, fuselage aerodynamics, okay, and then any external bodies, aerodynamic surfaces, then gravity, all. So, what you do is you take all the loads, transfer them to the CG. So, you will write Fx equals mass of the helicopter times this. Fy is mass of the helicopter, Fz is this. That means you have 3 force equations. So, you have Fx is u dot minus Rv plus Qw, but what normally done is the gravity load, you write it separately. So, you will get, I am putting it, because please note that gravity load acts along Z earth. Okay. So, you transform the Z earth to body, okay, and that will come, and then Fy, because this is the standard way of writing, V dot minus P W plus Ru minus mg sin phi cosine theta, and then Fz is mw dot Qu plus Pv minus mg cosine phi cosine theta. So, these are my 3 force equations, okay. Because if you look through the transformation relation, you will find that this is very obvious, okay. All right. Now, you have to get the rotation equations. Rotation equations are a bit messy, because you know if you have done rigid body dynamics, you know that angular momentum is given by I omega. So, I am writing here Hx, Hy, Hz, because angular momentum is a vector okay. This is a symmetric matrix, okay. Iyz minus Izx, Izy, Izz, sorry, the P, Q, R, okay. This is my angular momentum of the body, okay, H vector. So, Hx, this is along the body axis, please note that, because this can be derived. I am not going to the derivation of this, because this you must have done in the rigid body dynamics. Angular momentum, and the axis system is the body axis system. That is why in any aircraft, anything, you first decide your axis system, and then Ixx, Iyy, all these quantities are defined with respect to that axis system. Now, imagine if you put a load, if you put some equipment, your inertia will change, okay. That is the reason for using body fixed axis system, is only to simplify the moment equation, otherwise it will become really messy, because these quantities they do not change, you say, with the body fixed system. Of course, if fuel is expanding, it is changing, but you do not bother about that. So, this inertia, this is the inertia tensor. I hope you know that this is the 3 by 3 it is known as inertia tensor, okay, because this follows the tensor transformation, that is all. Now, what I want is what is the moment? This is defined with respect to my axis system in the body PQR. Now, I want moment. Moment is essentially h dot, this is about the CG, okay. This is about the CG, if you want I can put it the CG. H dot moment about the CG plus omega cross h, okay, because these vectors they are also changing with time. Therefore, when I take a derivative of that, I will get a omega cross h. Okay. So, this is my moment equation. So, I may put CG. That is why always you take moment equation about the center of mass. Okay. It makes it simpler. Now, what you do is, this is the moment due to all the external loads. Anyway, the gravity passes through the CG, so it will not create any moment. You have to take a dot product of this, which means you expand the whole thing, take a dot. Dot means P dot, Q dot, R dot, that will come. Then omega cross H, omega is PQR, okay. H is also a function of PQR. So, you have to take the cross product, write the full equation. That is the correct exact way. But usually what happens is they make certain assumptions. The assumption is, if you write the full stuff it becomes a little messy. So, I will leave that part. I will make the simplified assumption. The cross product of inertia, that is these quantities, okay. If it is a symmetric body, okay, if it is a sphere, perfect sphere, then the cross product is 0. You will have Ixx, Iyy, Izz, okay. But if it is a symmetric body about one plane, which is the longitudinal plane, if you take, then what you will have for every plus y, you will have a minus y, okay. So, wherever y is there, they will go off. That means, these quantities they will go to 0, but this will stay Ixz, because they say that number for hell is for aircraft or anything is substantial. Even though this may not be 0, Ixy, Iyz, you neglect it. But if you do not want to neglect, carry the entire term. It is not very difficult. If you have a computational aspect, you can carry it, it is not a problem. But for ease of understanding, they try to throw away a lot of things and then try to get a simplified version. Now, I will write generally all cross products except Ixz, that means these are neglected, okay. That is because you say, but in the aircraft case, yes, there is a symmetry, but in the helicopter it is not exactly symmetric, because your tail rotors sticking around one side. But you say that it is all right, let me make that assumption, because then it becomes, I can write it in a small. So, I will have my mx is moment of the all the loads, that is the rotor loads, tail rotor, horizontal surface, every aerodynamic load, whatever you get, inertia, aerodynamic load, everything, transfer it to the CG. That is the, along the x direction is the mx. That is why we get Cmx, Cmy, Cmz, all those things, the rotor, they transfer to fuselage center of mass. This becomes P dot minus Ixz, because I made the assumption R dot plus PQ minus QR into Iyy minus Izz, and then My is Iyy q dot minus I x z r square minus p square minus r p I z z minus I x x, then m z I z z r dot minus I x z p dot minus q r minus p q I x x minus I y y. Okay. These are my, and normally you see I x z is comparable to I x x magnitude wise. So, this has to be, that is why weights and CG group in any aircraft industry or aircraft or aerospace, any company, they have to get these values, okay, before the aircraft is built. It is like you make estimate from the drawing and then you try to calculate the complete IXX, IYY, IZZ, all these numbers for a given coordinate system, because if you make a mistake there, your flight dynamics is all wrong. So, this is done, that is why sometimes it is a routine job, but one has to do it in an aircraft industry. As a matter of fact, all your dynamics is only this, but of course, I made an approximation. If I do not make approximation, that is all the full dynamics of a rigid body, there is nothing more. Okay. Beyond this, all problems, whatever you have learnt in physics 101 or dynamics, you can solve with this set only. Only thing is you must be very clear. Okay. Now, you see how do I solve? I have 9 equations. How do I solve for my problem? Because what are my unknowns of the problem? Okay. First you say, hey, I am going to fly a steady maneuver, and subsequently I will say, if there is a perturbation about the steady state, what is the stability? Only these two are solved using these equations. Otherwise, this is a fully nonlinear equation, because you see p square, r square, p q, everything is nonlinear. So, solving it is not that straightforward. So, how do they attempt to solve this problem? In the case of helicopters, I will go to the helicopter thing. See, what is done is, first I say I am doing a particular flight condition. That means I am not accelerating. My u, v, w are fixed, p, q, r are also fixed, which then I will write my u is u equilibrium plus delta u, which is a, and v, which is the v equilibrium, and w equilibrium delta w time, and then p equilibrium plus delta p q and r equilibrium plus delta r time t. Okay. Then you need to have also your theta equilibrium, phi equilibrium, because theta and phi, that is the orientation of the vehicle. So, I will have theta is theta equilibrium plus maybe delta theta, and phi, which is the phi equilibrium plus delta. Okay. Except psi, because there is no psi equilibrium, because the orientation can change as the helicopter turns. My angle this side, it can keep on turning. There is no equilibrium for that. Okay, please remember, that is why that turn we allow, because it is like a yaw rate pretty much, it can keep on turning. But the vehicle orientation is theta equilibrium, phi equilibrium there. So, what you do is you substitute these quantities now in this equation, okay, and then you say my deltas are small, product of deltas I neglect, okay, and I will collect all the terms with the equilibrium quantity separately and collect all the terms with the delta separately. Now, I will have one set of equations, I call it as the steady state equilibrium equation, and another is the perturbation equation. Okay. Perturbation equation, I need to use it for my stability, whereas equilibrium I use it for my trim. Okay. This is how it is done, otherwise you will go nuts. This is a highly complicated formulation, you just cannot get anything. Okay. First you split, when you split you will write the equilibrium equation. So, I will just write that equilibrium force equation. Okay. So, you understand this, you substitute here, then take. So, when I take u dot, that means it is only delta u dot, u equilibrium is constant value. Okay. Now, I can write my equations. This is force equation and m minus r equilibrium v equilibrium plus q equilibrium w equilibrium plus mg sin theta equilibrium is x equilibrium, that is the force along x direction equilibrium force, that means the steady state force, that is what it means. M minus P equilibrium, W equilibrium, R equilibrium, U equilibrium minus, sorry, I should put a minus mg sin phi equilibrium cosine theta equilibrium is y. Then the z equation minus q e u e plus p equilibrium v equilibrium minus mg cosine phi equilibrium cosine theta equilibrium is z. Okay. Then you write the moment equation also, 3 moment equations, that is moment, you will have minus I x z p equilibrium q equilibrium, I y y minus I z z q equilibrium r equilibrium, and this is the standard notation L E roll, this is roll equation, and then minus I x z r square minus p square equilibrium minus I z z minus I x x r e equilibrium p equilibrium is m, you may say equilibrium, this is pitch, and then the yaw equation is I x z q equilibrium r equilibrium. minus Ixx Iyy P equilibrium Q equilibrium, which is N Eq, which is the okay. And then you have to change this equation also. In this equation, because you know that these are dots, so dot means that is the time derivative. So what will happen is P equilibrium is minus psi dot equilibrium theta equilibrium, Q equilibrium will be sin phi eq cosine theta eq, and then R eq becomes psi dot equilibrium cosine phi equilibrium cosine theta equilibrium. Now you see this is my full equation, 9 equations, okay. Here, 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 no, this is Ixz, no minus sign, okay. Now you see these 9 equations you have to solve. What are the quantities which I have to know? Now I will show this because I would like to come here, which will be the 9, sorry not 9, the unknown quantities of the problem. What are the unknown quantities? Because when I want, these are 9 equations, what are the things I do not know? You say mass of the helicopter, you know, please note that, that is a very important. I know the mass of the helicopter, I know the inertia properties, the tensor. External loads, these are my rotor loads and fuselage aerodynamic loads, any horizontal surface, any lifting surface, everything, they provide those loads here. I do not know what is UE, VE, WE, I do not know that. Angular velocity, PE, QE, RE, I put a capital because for equilibrium I just used a capital here, that is all. Otherwise it is the P equilibrium, Q equilibrium, all the E is equilibrium. Then this is the turn rate, psi dot, and orientation angle, theta equilibrium, phi equilibrium, and then control input 4, okay. So I have 13 quantities which need to be known, but I have 9 equations. Therefore, you have to prescribe 4 quantities before you really can solve the problem. Now, what are those 4 quantities you will specify? You will not specify 4 from here, that is the problem. The 4 quantities which you specify are flight speed and the flight path angle. I will tell you what the flight path angle is. Then turn rate, psi dot, and then you will say what is the side slip angle. Okay. The definition for side slip angle, sin beta is VE by VFE. Please understand, now the quantities which are mentioned there are different from, except this. This is different, this is different. I do not have any, I do not have VFE defined there. You follow? I do not have gamma FE defined there. I have only UE, VE equilibrium quantities, but what I specify is in some other 4 quantities. Okay. Now, you have to relate these 4 from here to some of those quantities. That is again I will briefly describe. Okay. I think maybe I will go back to the first figure. Okay. If it is there, I will specify that. What we need is, this is the Z earth axis. Okay. Body axis is xb, yb, zb. Okay. And velocity vector of the body is v bar fe. The components of this are ue, ve, we, they are equilibrium quantities. Components of the velocity vector along the body fixed system, please understand, is u equilibrium, v equilibrium, w equilibrium. Now, the flight path angle is defined as, this is the z earth, x earth and y earth. The velocity vector can be in any orientation. Okay, it can be up, down, anywhere. What you do is, you project this velocity vector onto a horizontal plane, onto the horizontal plane. Okay. Project this vector onto the horizontal plane, and then the angle between the vector, velocity vector and the horizontal plane is the flight path angle. Okay. And then you project it, and the angle between the projected vector and the x earth, you call it as a chi. Just put some, because that will come later. Okay. Now, these are your quantities. I have the velocity of the vehicle. I do not know what is the chi is, but flight path angle I specify. Velocity I know. That means I know this and I know this, but I do not know this. Okay. But from here, if you look at it, I know omega e, that is the turn rate, but I do not know ue, ve, we, none of these quantities I know. Okay. Now, what you do is, you take the velocity vector, transform them along the earth fixed system. Okay. First, that means I have the velocity vector, I am going to get components along the earth fixed system, because this is a little interesting, but finally you will not use that. The velocity vector in the earth bound system, okay, is u earth is VFE cosine gamma FE, this is the flight path, and cosine chi, this is not psi, this is chi. Okay. And then VEA, VFE cosine gamma FE sin chi, and then W earth is VFE sin gamma FE. This you can get, only thing is you do not know what these quantities are. Okay. Mathematically I can write it, but I know this, given this sin gamma FE, I know WA. Now, what you do is, you go back, transform this in the body fixed, because you know the transformation relation between this and the body. When you do that, you will get, now I am writing for, okay, I will write it for one quantity, UE is VFE cosine gamma FE cosine theta equilibrium cosine chi cosine psi equilibrium plus sin chi sin chi, this is psi equilibrium, minus sin gamma f e sin theta equilibrium. Okay. You will find this is the exact transformation in UE or U equilibrium, sorry, we are using equilibrium, right. Okay. What you will find is you will have a term cosine cosine plus sin sin. Okay. This is nothing but you call it by chi e is chi minus this you call it track angle. Okay. This is something new, track angle. Okay. That is why you do not define it, but later you will get the track angle will come. You have to solve for the track angle. Now, if I write in this my u equilibrium in the body, because this u is in the body axis system, I will have it in this form VFE cosine gamma FE cosine theta equilibrium cosine chi, maybe I will put, if you want equilibrium you can put equilibrium minus sin gamma FE sin theta equilibrium. Okay. In a similar fashion you can write VEQ. I will later tell you what is why I am using, because in the equilibrium state you say that my velocity is constant, flight path angle remains constant, orientation angles are constant, and this is also constant, they do not vary with time, but you will find chi and psi. What is psi equilibrium? There is nothing like psi equilibrium. It is also changing with time. So, I can't put a psi, because you said psi dot has an equilibrium, that means psi cannot have an equilibrium because it is turning. So, usually what is done is you do not try to put a equilibrium here, you say these two quantities are varying with time, but their difference is a constant. Okay. Both of them are varying the same amount, the difference is a constant. Okay. And now you have to get that. Now flight mechanics possibly they may, because the track angle is. Now what you do is you will have your VE is VFE cosine gamma FE sin phi equilibrium sin theta equilibrium cosine chi equilibrium plus cosine gamma FE, because these are all long expression, phi equilibrium sin chi equilibrium plus sin gamma FE sin phi equilibrium cosine theta equilibrium. Okay. Similarly, you will have W, because the combination it comes such a way, here this sin chi, you will have, if you substitute this you will have sin chi cosine psi minus something. So, that is how that expression will come, that is why they will come out to be sin chi and cosine chi. Okay. Now, you will have W and your W equilibrium will be again VFE cosine gamma FE cosine phi equilibrium sin theta equilibrium cosine chi equilibrium minus cosine gamma FE sin phi equilibrium and then sin chi equilibrium. Then you will have one more term plus sin gamma Fe cosine phi equilibrium cosine theta equilibrium. Okay. Now, you see, for me to get UE, VE, W equilibrium quantities, I know flight path, the velocity I know, the flight path angle is given. Okay. What I do not know in this is, I do not know chi, I do not know theta, I do not know phi. These three equilibrium quantities I do not know. You follow what I am saying? That means, if I want to get the velocity along the body axis, given the quantities of these four, I still need to know three: chi equilibrium, theta equilibrium, phi equilibrium. So, what do I do is, I first go and solve for how I define my chi equilibrium. Okay. What is given here is sin beta E, because side slip angle is specified. You have to specify what is side slip. Side slip angle is what? This is V equilibrium in the body system. Okay. Whether you are moving along the y body, along the y axis of the body system. If you have a velocity there, the ratio of that velocity to the total velocity resultant, that is my side slip. That means, side slip angle is specified, that is a given quantity. Now, you know from here V equilibrium, V by VFE, this is nothing but sin beta, which is the side slip. So, I write sin beta E, this entire expression, okay. That is sin beta E is cosine gamma Fe sin phi equilibrium sin theta equilibrium cosine chi equilibrium, then plus cosine gamma Fe cosine phi equilibrium sin chi equilibrium. Maybe I should put it, okay, plus sin gamma Fe sin phi equilibrium cosine theta equilibrium. Please note that here, okay, what I will do is, I know this quantity I know. I can form a quadratic equation in sign of them. Okay. Call this K1, K2, K3 and then take this term sin square, cos square, something chi. You solve that quadratic equation. Okay. You can write it as K1 cosine chi equilibrium plus K2 sin chi equilibrium minus K3 equals 0, okay, because you bring this term here. Okay. You can say this is K1, this is K2, and K3 is you bring this term and then put a minus sign. Now, what you do is you convert either sine to cos or cos to sine, okay, and then take this term on this side, this term on the other side, square both, you will get cosine square, then this is sine square can be or cosine square can be written as 1 minus sine square. So, you will have an equation in sine chi. So, finally, you will write sine chi equilibrium is given by K2 K3 plus minus root of K1 power 4 K1 square K2 square minus K3 square K1 square over K1 square plus K2 square. Okay. This is what you will get. That means there are two roots, you always pick the meaningful root, that is what is done. What you know in this is knowing beta E side slip angle, and you have to assume phi equilibrium, theta equilibrium, and then these are assumed, gamma Fe is given. Okay. That means, when you are starting, you specify those 4 quantities. First thing is I must go and get the track angle. How do I get track angle? First I solve, I assume the orientation of the helicopter. You assume, then you get the track angle. Once you get the track angle, you have already assumed these two. Track angle you know, gamma Fe you know, you can immediately get UE, VE, WE. That means, you have all the 3 quantities, okay, and given psi dot, that is the input equilibrium turn rate. You have already assumed theta EQ, PEQ. That means, I know PE, QE, RE. Okay. You go back the 6 equations and then solve. I will just briefly mention, because this procedure is quite a complicated, that is where the convergence all this. See here I briefly describe the procedure that is done. Trim procedure I just put it complex. Given the data, okay, velocity, flight path, and then turn rate, side slip. Once I have this, I go back and solve first the track angle, but assuming theta EQ and phi EQ. So, that is why assume, I say here these 4 quantities are pilot control input, I assume these 2 quantities which are EQ, compute the track angle. Once you get the track angle, obtain U equilibrium, velocity equilibrium, W equilibrium, then P, Q, R. There I use capital, here P, Q, R. Okay. Then you solve rotor inflow. That is the, you may assume uniform inflow or any other inflow, first assume that. Go and solve rotor inflow. Once you get the rotor inflow, then you solve the blade equations. Even if you have only flap equation, just solve the, but you should write the flap equation based on a hub which is having all these motions, because you cannot use that level flight flap equation. So, your flap equation must contain the hub motion, that means all the equations you have to develop. Then solve the blade flap, assuming only flap. If you have lead lag, torsion, everything, then you have to solve the full. Get the rotor hub loads and other aerodynamic loads, transfer them to the fuselage, get the force and moment equilibrium, you will find that they do not match. Okay. But you take the average load, please understand, you do not hub loads only you get, obtain the rotor hub loads, that means you take one revolution, get the mean values, then transfer the mean values for balancing the force and moment. It will not balance. This you have 6 unknowns, which are these: pilot input and orientation of the vehicle. So, 6 equations, you use these 6. Okay. Now, once you get this, you go back here, because for getting the blade loads you need the pitch input, otherwise you cannot get the blade load, right. That is why you assume this. Once you get a new update, go back here, again compute the track angle, again calculate all the UE, WE, and then you do this. Okay. This is a quite a complicated procedure, sometimes the program will not converge. It is very tricky problem. Okay. And this is the complicated trim procedure. Pardon? No, it is not how long, it is actually the convergence becomes a complicated problem. See, we are going to do this because we have developed the equations, now we plan to do, but initially we will do a steady turn. Okay, do not go and complicate all sorts of motion, just give a, we have done for a flap, we did a steady turn and we are getting results which are quite similar to what are obtained by some other people. Now, we want to do more complicated motion. Ultimately, the problem is the industry required, hey, if I give a control input, how my vehicle will perform. That one is you can go and solve my linearized, that delta u, delta v, delta w, that equation, that is the perturbation only. Okay. But that is will give you only at the instant what is happening. It will not tell you over a long time, because long time, however you would have done the equilibrium about a hovering condition and a perturbation about the hovering condition. But you go to forward flight at some other speed, then you will have an equilibrium and a perturbation for that. Like that you will have equilibrium, perturbation, equilibrium, perturbation. You cannot say this perturbation will lead to that perturbation. If you want to solve the full problem, you have to solve complete nonlinear problem. And this is where in between you have to get the rotor inflow, please understand. This is also equally complicated problem, because rotor inflow is related to rotor thrust. Okay. So, you can have various types of inflow models, dynamic wake model, and we have incorporated something which is Dries model you can put, but that is again a constant, even though it varies along the radial and azimuth, but it does not vary with time. So, you can have different types of inflow models. So, usually these problems first you try to solve in a simplified way, take only flap, check whether a program is converging, because you will be able to get the mistakes from there. Once it is done, then you can say, okay, these are my loads, and if you want to include stall model, please understand, when I get the aerodynamic load, I should have stall model for the blade. All those things must be, I cannot have a closed form expression, everything has to be integrated in this part. So, that is why the aeroelastic problem is part of flight mechanics problem. It is not that this is an independent problem in helicopters. And if you are doing this kind of a maneuver, this is a real challenging problem. Okay. I think with this we close.